Greetings everyone. This video is about our MT project, Skid Steering Mechanism Implementation in Assembly. My name is Yashjinder and my partner is Vishnu Kumar Shukla. So what is skid steering mechanism? In this mechanism, the wheels on each side of the vehicle can be driven at different speeds in forward or reverse direction. All wheels on a side are driven at same rate. This leads to slipping or skidding of wheels and hence its This mechanism is used in tracked vehicles like tanks, bulldozers, and Martian rovers. A microprocessor is used to control the speed of motors or wheels. Input to the microcontroller may be provided by a joystick or a general purpose controller. If closed loop system is used, then it can also be used for autonomous navigation. There is an excellent resource on web by Snapcraft where they have calculated the speed of left and right motors to achieve the skid steering mechanism. For straight line motion, both sides of motors can be commanded with same speed in same direction. But what about turning the vehicle? For turning, we can rotate both motors in opposite direction. This will fulfill our needs. If we combine these both methods, namely straight line motion and turning, we can achieve long left turns and long right turns as well. If linear velocity commanded is x and angular velocity commanded is z, then left wheel velocity can be represented as x minus zt by 2 and right wheel velocity can be represented as x plus zt by 2, where t is the distance between the two wheels. In X16F8778 for this project, we are using 8-bit resolution. Although it supports 10-bit ADC, but calculations are easy in 8-bit. MSB is used for sign determination, like for positive velocity or negative velocity. And so we are left with only 7 bits for magnitude. PIC does not support division. So for calculations, we are using 0.5 meter as track length, as the angular velocity is multiplied by t by 2, so it becomes 0.25. Like for in PIC, we have to right shift by 2 bits to achieve z into t by 2. 100% duty cycle is achieved at 160. Like linear velocity maximum value would be 128, and the angular velocity maximum value will be zt by 2, that is 128 into 1 by 4, so it's 32. And 32 plus 128, like linear velocity plus angular velocity would be 160. Here is the code for the skid steering mechanism. These are the configuration bits. These are general purpose file registers which have been used in the whole project. So like delay 0 is used for storing the linear velocity that is commanded, and similarly delay 1 is used for storing the angular velocity commanded. Delay 2 is used for storing the signs of commanded velocities and the direction of rotation of wheels. Delay 3 stores the magnitude of the velocity of left wheel, and delay 4 stores the magnitude of velocity of right wheel. So initially we are setting port A as input, and port B and port D are used for debugging purposes only. Port C is the output port, which also constitutes of 2 CCP pins for PWM generation, and ADCON 1 is initialized in such a way that the 0th and 1st bit of port A are analog inputs, and the 2nd and 3rd bit of port A are used as references voltages. So PR2 is initialized with value 160, that is the time period of the output PWM signals, and the CCP1 con and CCP2 con are configured as PWM output signals, and T2 con is initially kept off, and the ADCON 0 is initially set to channel 0 for ADC conversion. So using a loop, ADC is taking place. So like in this we are checking if the ADC is completed or not, so we will go out of the loop. So in this code we are normalizing the data into 8 bits, as the incoming data is stored as 10 bits. So we are taking 2 right shifts to make the data in 8 bit, and after that we are switching from channel 0 to channel 1 for ADC conversion on channel 1, and similarly checking if the ADC is completed. Then we again are normalizing our data from 10 bits to 8 bits using 2 right shifts, and then the received data would having a range from 0 to 255, but for negative velocities we have to convert it into negative also. So we are subtracting 128 from the received data to convert its range from -127 to +27. So like then we are checking if the velocity commanded is negative or positive. So if it's positive, then we are using 0th bit of delay to store the sign of the incoming data. Similarly, the first bit of delay T2 is used if the angular velocity commanded is negative or positive. So if bit is 1, that represents the incoming data is negative. Then we are performing the function zt/2, where we have to only by 2 bits to multiply it by 1 by 4. Then the main code comes here when we have to compute the speed of left. So according to the sign, we have made different cases. So like in this case, when both the linear and angular velocities are positive, as the speed of left wheel is x minus zt/2, where x is linear velocity and z is angular velocity. So when both are true, then the direction will depend whichever term is bigger. When linear velocity is positive and angular velocity is negative, then both will add up and the direction will be positive. When linear velocity is negative and angular is positive, then the sum will come out to be negative and the direction will also be negative. When both the commanded velocities are negative, then also the direction will depend whichever term is bigger. Then similarly, the calculation of right wheel, only difference is that right wheel velocity is x plus zt/2 instead of x minus zt/2, which is in the case of left wheel. So there are different cases for right wheel as well. And then depending on the sign, we are commanding the direction for the left wheel as well as the right wheel. This is for the right wheel. So like PWM also supports 10-bit resolution, but we are only using 8-bit. So we are again using 2 redshifts to convert the 10-bit PWM data into 8-bit data. So this is for left wheel and this is for right wheel. CCP1con and CCPR help registers are used for putting the PWM data. Similarly here CCP R2L and CCP2con are used for PWM data. Then we are starting our timer 2 and using loop we are checking if PR2, that is 160, that the value we have put in the PR2 equals the timer 2 value. If that happens, then we again go to the loop and starts the timer again from 0. So in this way our PWM signals are generated. So here is the Proteus simulation. If we want our vehicle to move in a straight line in forward direction, then we can command linear velocity as maximum voltage and the angular velocity as 0 voltage. So both the motors will move in the same direction with same speed. Similarly, if we want our vehicle to move in the backward direction, then we can command the maximum negative velocity and the motors will move with same speed in opposite direction. If we want the vehicle to turn around its axis, then we can command 0 linear velocity and the angular velocity as maximum. And now we can see the motors move in opposite direction so that the turning can take place. If we want to move in a reverse direction for turning, then we can command negative velocity as angular velocity, and then the motors will again turn in opposite direction with each other and the turning would be opposite to the previous case. Now for long left turns and long right turns, we can combine both these velocities. So like if we can consider this as this motor as right wheel and this motor as left wheel, so that now we can see that velocity of right wheel is more. So like this is a long left turn. In this case, the velocity of left wheel is more and right wheel is less. So it is a long right turn.